You've probably heard of Schrödinger's cat. A cat is placed in a box with a mechanism that has a 50% chance of killing the cat. Until the box is opened, the cat has an equal chance of being alive or dead. According to this thought experiment, the cat is actually alive and dead until we open the box to observe the cat. But why? Well, the answer is actually much smaller than this analogy, and is also a much discussed topic in quantum physics. In fact, the creator of this analogy, Erwin Schrödinger, actually created it to criticize the principles based on his own discoveries in the field. He actually ended up getting so tired of quantum physics he would become a biologist. But what did he discover that led him to create this thought experiment? And why did it gain him the name the father of quantum physics? Let's zoom in, even more, down to the quantum level to understand. This is an electron. Electrons are similar to light in the fact that they move both as a particle and a wave. These particles follow a microscopic wave motion in which they move extremely fast, making them extremely difficult to monitor and actually completely impossible to entirely predict. This is explained under the Heisenberg uncertainty principle. This principle states that one can't know the velocity and position of a quantum object at the same time. The two actually function as an inverse ratio. The more we know about the position of the particle, the less we know about its velocity, and the more we know about the velocity of a particle, the less we know about its position. This means we can't know the exact position of a particle, but it could be going any speed. Or we can know the exact speed of a particle, but it could be anywhere. The equation form of Heisenberg's uncertainty principle is delta x delta p is greater than or equal to h divided by 2, and almost always uses extremely small numbers expressed in scientific notation. H represents a shortened Planck's constant, or h divided by 2 pi. Heisenberg's equation calculates the margin of error in the position or velocity of an electron or other quantum particle. It also creates the context of superpositions, which is what Schrödinger's cat aims to explain. Until we look at the electron in a frozen frame of time, we have no reference for its position except for where it's allowed to be. For example, if an electron were in a box, it's allowed to be in the box, but not in the walls of the box or outside of it. While it's inside the box, the particle could therefore be anywhere within that box that we know it could possibly be. But because of Heisenberg's principle, and us not knowing the electron's position or speed, the electron is not just mathematically unknown in position, but simultaneously everywhere it could be at once. Until the electron is observed, the superposition remains, and we can prove that they act in this way. In a famous double-slit experiment, scientists observed that an electron, when shot through a wall with two slits, can simultaneously pass through both slits of the wall at one time. However, once we see the electron, we know where it is and the superposition collapses, as Heisenberg's uncertainty principle now dictates that we somewhat know both the speed and position of the electron. The area of probability an electron could be is called a probability cloud, and Schrödinger's equation predicts the probability cloud of an electron ending up in any one place. It's a differential equation, meaning it doesn't give a final answer, but an equation that can then be used to predict the electron cloud. When we use the equation we get over and over again, it gives an idea of the probabilities of an electron being in a certain place, even though we have no guarantee it will be there, and a superposition therefore occurs. The most important variable in this equation is psi, which represents the wave function. It takes the position and momentum of an electron, and when squared, it gives the probability of location. So why did Schrödinger criticize his own math? Well, he actually criticized the Copenhagen interpretation, stating that superpositions couldn't exist just as a cat can't both be alive and dead. However, as scientists found proof of superpositions, the thought experiment became more of an analogy for how the science actually works. Schrödinger's cat has even more interesting implications too. It creates implications of parallel worlds. When we observe the cat, we now know it's dead. However, this also creates an alternate timeline that happens when we look at the cat and learn that it is alive. These are now two parallel realities that we begin once we observe the cat, and we have no proof that these alternate realities do or do not exist. A theoretic principle such as this being based in science sparks extreme interest, but does lead into some of the most complicated math used to understand our physical world. For this, it's no wonder Schrödinger decided to study biology instead. But many took his place, and innovation continues to thrive, regardless of if the cat is dead or alive.